What's up, Chem Peeps? Let's take a look here at just two quick problems to get you to think about how you can choose the correct acid-base indicator for your titration. In this first example, we're provided with a titration curve, and we are asked, of those listed, which indicator would be best for the titration whose curve is shown above? First thing we want to do is identify the pH at the equivalence point in this titration. As I do that, I recognize that my pH at the equivalence point is going to fall somewhere between pH 10 and pH 11. Of the acid-base indicators provided, I'm going to choose the one that has a pKa that is closest to the pH at the equivalence point. As I scan my answer choices, my best option, phenolphthalein. It has a pKa of 9.4. Keep in mind that the pKa of an indicator is equal to the pH at the midpoint that we observe its color change. All right, moving right along. Let's take a look at this last example. It says, which of the following indicators would be most suitable for the titration of 10.0 mils of 0.10 molar lactic acid with 0.10 molar potassium hydroxide? We're told the pKa for lactic acid is 3.08. Okay, now this one is kind of a doozy, and I'm gonna work through how you would come up with the answer pretty quickly. It's putting together a lot of the information that you've learned about so far this unit. Once I've done that though, I'm going to come back and show you a shortcut to help you answer this question. First, I'm going to write out the equation that represents the neutralization reaction that occurs in this titration. Boom. So at this point, you should recognize this is a strong base, weak acid titration. So the pH is not going to occur at pH 7. It's going to occur slightly in the basic range. And if I'm going to try and choose an indicator, I need to choose an indicator that has a pKa that is equal to the pH at the equivalence point. So I should be able to throw out answer choice C and D right away. So let's determine what the pH will be at the equivalence point. Because it's strong base, weak acid, the anion of my salt is going to be what contributes to the pH at the equivalence point. So let's do this. First thing I'm going to do is use my molarity equation to determine how many moles of lactic acid has reacted. Boom. Quick jump to my calculator. 0.10 I've reacted 0.0010 moles of lactic acid. Based on my stoichiometric ratio, that means that I've also produced 0.0010 moles of my salt and conjugate base lactate ion. Boom. And the concentration of my lactate ion is going to be my number of moles, 0.0010 in 20 milliliters. Why 20 milliliters? Because I had 10 mils of lactic acid originally, and I will need 10 mils of my strong base to neutralize all of it. So I have 20 milliliters total, which means that the concentration of my lactate ion is equal to 0.050 molar. Because this ion is acting as a weak base, let's set up an ice table. Boom. Now let's write our expression for Kb. Boom. Let's determine the value of Kb from the Ka that was provided. 14 minus 3.08 answer seconds log negative answer. 1.2 times 10 to the minus 11 is our value of Kb. Plug in our equilibrium concentrations. I'm going to make the x is small approximation as I go. Boom. Solve for x. Times 0.050 answer. Second square root second answer. X is equal to 7.8 times 10 to the minus 7 molar. That is our hydroxide ion concentration. If I take the negative log of my hydroxide ion concentration, I will solve for the pOH. Boom. Then finally, to determine the pH at the equivalence point, I'm going to use this relationship between pOH and pH. Boom. So the pH at my equivalence point is 7.9. As I take a look at my indicators, the pKa of the indicator that's closest to the pH at my equivalence point, phenol red. Boom. Done.